Okay, so this is part 2 of the video. So in part 1 we left off at this point here. So when we plugged our series into the differential equation and simplified, we ended up with this result here. This has to equal 0. So this means that all the coefficients in front of the x's would have to be 0. So in particular, the r times r plus 1 times a0 would have to be 0. The r plus 1 times r plus 2 times a1, that would have to be 0. And this guy would have to be 0. So equating coefficient implies then we get the following equations. So again, equating coefficients, then we must have these equations. So the first guy needs to equal 0, the coefficient in front of the x to the r minus 1. And this guy is from the coefficient in front here, that is equal 0. And this is the coefficient in front of the x to the k plus r plus 1, needs to equal 0. Okay, let's move the ak over here and then divide by this. Let's solve for a of k plus 2. So doing that, we get then okay, so first I subtracted ak on both sides here, then divide by this to solve for a k plus 2. So we end up with this as a recursive relation. And now here we have to find conditions on r that make both of these 0. We have freedom over the a0 and a1 also. But we can't choose both of them to be 0, because if you chose both to be 0, that would make the whole thing 0. So there's two cases to consider. Let's look at the two cases here. So here's our two cases. There's actually more than two cases, but we're going to show that each of these cases will lead to a different power series. And we're looking for two solutions here. Okay, so if I chose r to be minus 1, say, that would make that one true because you have an r plus 1, so putting minus 1 there, be minus 1 plus 1, so that'd be 0. And that'd be 0 also. And that means you're free to choose whatever you want for the a0 and a1 because minus 1 makes this one 0 and this one 0. But so I can choose a0 to be non-zero and just choose it to be 1 then for convenience. And then choose a1 to be 0. Or I could choose a0 to be 0 and a1 to be 1. Okay, so let's consider case 1 first. Okay, so we're going to look at case 1. So r is minus 1. So put minus 1 in place of r over here. a0 we're going to choose as 1 and a1 we'll choose as 0. So plugged in here. And now, since a1 is 0, and this recursive relation relates ak to ak plus 2, so therefore a3 I claim would be 0 because that's when k is 1 here. But a1 is 0. So pretty much I claim that all the odd terms, so the 1, 3, 5, 7, and so forth, will be zeros because a1 is 0. We can show it in a second. And I claim all the even terms will not be 0. So let's stick in a few terms here. So let's say let k be 0. So if we choose k to be 0 in our recursive relation over here, you'll have then put 0 here, you'll have a2 on this side equals, putting 0 here, negative a sub 0 divided by putting 0 here, it'll be 1, putting 0 here times 2. And 1 times 2 is 2, but you can also think of it as 2 factorial. I'm going to write as 2 factorial. And our a0 is 1, so it's going to be negative 1 over 2 factorial. Now, knowing a2, I can find the one 2 higher because it relates ak to ak plus 2. So letting k be 2 next, we can find a4. So let's do that. So choosing k to be 2 now, plugging it up here, you'll have, then put 2 there, the a4 equals negative a2 over putting 2 here, 2 plus 1, putting 2 here, 2 plus 2. And you can write that as negative a2 over 1 over 3 times 4. Now a2 is up here. It's the negative 1 over 2 factorial. So there's not a minus sign, so 2 minus signs will make a plus. So it'll be 1 over 2 factorial times 3 times 4. But 3 times 4 times 2 factorial would be 4 factorial, so it's 1 over 4 factorial. Okay, so that's when k is 2. Alright, I'm out of space here, so let me erase a few things and we'll continue. So summarizing, we have this. Here's a recursive relation. We have under case 1, we have a0 is 1, a1 is 0. We found that a2 was negative 1 over 2 factorial, a4 is 1 over 4 factorial. That's when k is 0, k is 2. So we're choosing k to be even numbers, so the 0, 2. So next one would be k is 4. So doing k equals 4, we get then so when k is 4, we'll have then, putting 4 here, ace of 6 equals negative ace of 4 over 4 plus 1, 4 times 4 plus 2. So you can write it as negative a4 over times, 1 over 5 times 6. And a4 is up here, so it's going to be minus in front, so it'll be minus 1 over 4 factorial times 5 times 6. But 5 times 6 times 4 factorial would be 6 factorial, so it's going to be negative 1 over 6 factorial. Okay, so we can probably start to see a general pattern happening here. So it went 1 over 2 factorial, negative 1 over 2 factorial, 1 over 4 factorial, minus 1 over 6 factorial. So you can probably guess the next one, when k is 6, should be negative 1 over 8 factorial. Let's just show that, and then we'll try and find a general pattern. So let's do k equals 6. Okay, so when k is 6, then we'll have, so putting 6 here, it'll be a8 equals negative a6 over 6 plus 1 times 6 plus 2. Right, is negative a6 over 1, negative a6, sorry, times 1 over 7 times 8. And the a6 guy is negative 1 over 6 factorial, but there's a minus sign. So it's going to become plus 1 over 6 factorial times 7 times 8. And 7 times 8 times 6 factorial is 8 factorial. Okay, so it went negative 1 over 2 factorial, 1 over 4 factorial, negative 1 over 6 factorial, 1 over 8 factorial. So you probably guess the next one should be negative 1 over 10 factorial. Let's try and write the general one right here now. So here's the general one. So in general, I claim that a sub 2m will equal negative 1 to the m over 2m factorial. So that should describe the pattern that we're seeing here. So let's just check when m is 1, we should end up with this one. Let's see. So let's note that. So when m is 1, so it'll be a sub 2, so putting 1 in place of m here, will equal n, according to this formula, negative 1 to the 1 power over 2 factorial, so negative 1 over 2 factorial, which agrees with this one, so check. When m is 2, then we should end up with this one. Let's just check that. So when m is 2 in this formula up here, you'll have then, so putting 2 here, a4 equals negative 1, 2 for m squared over 2 for m, 4 factorial. So it becomes then 1 over 4 factorial, which agrees with this guy up here. So check. And let's check one more, say, when m is 3. So when m is 3, so putting 3 here, I'll have a6 equals negative 1 to the 3 over, putting 3 here, 6 factorial, which is negative 1 over 6 factorial, which agrees with that one. And I guess we'll just do one more when m is 4. So when m is 4, we'll have then 1 over 8 factorial, so you can see the formula works. Okay, so you can see the formula works here, so I'm out of space. Let me erase a few things and we'll keep going. So summarizing, we have this. So we've shown the even terms can be written this way. That's Now I want to show that I mentioned already that all the odd terms should be 0 because A1 is 0. Let's just kind of show that here. So say choosing K to be 1. So when K is 1 then, so putting 1 over here, you'll have A3 equals negative A1 over 1 plus 1, 1 plus 2. But A1 now is 0. That's going to make A3 0. And let's do, say, when K is 3 next. Okay, so when K is 3, then you're going to have, putting 3 here, A5 equals negative A3 over 3 plus 1, 3 plus 2. But A3 was 0. So it's going to make A5 0. So you can see it's going to keep being 0 for all these odd terms. So in general we can say, that A of 2m plus 1, that just means an odd number, is 0. Okay, so now let's write the series solution for case 1. Okay, so now our series solution will look like this. Okay, and for case 1, we just shown that A of 2m is this guy, A0 is 1, A1 is 0, R is negative 1, and A of 2m plus 1 is 0. So plugging into this guy, we get then okay, so plugging our values into our series here, R is minus 1, the K then is 2m in our case, and it'll be m going from 0 to infinity. So just picking up the even terms here. Okay, I can pull so I got an x to minus 1 here, I'm going to pull it out in front. So doing that we get then, okay, so I pull the x to minus 1 out in front here, and this guy remaining here, you can note that actually this is the power series for cosine of x. You can look that up, but this is the power series for cosine of x, so therefore this guy can be replaced with cosine of x, so the answer then will be just cosine of x over x. This is the answer for case 1. So let's summarize what we have. So hence under case 1 then we have that the solution we found then, cosine of x over x, should be a solution of our differential equation here. Okay, now let's look at case 2 now. So let's consider case 2 now. So case 2 being R is negative 1, A0 now this time is 0, and A1 this time is 1. So this time it's going to pick up all the odd terms. So I'm just going to give you the answer and let you check it. So let you check the even terms will be 0 this time because A0 is 0. It's going to make A2 and A4 0. And the odd terms will be given by this formula here. So I'll let you check that. And then the series solution will be the following. Okay, so following the procedure similar to case 1, then plugging into the series here when R is minus 1 and stuff, it ends up being this. You can pull out the x and minus 1 like we did in case 1, and then you can notice that this guy here is actually the power series for sine of x, so therefore the answer here is sine of x over x. So this should also be a solution to this differential equation up here. So in particular we can write a general solution for this guy then, because we have 2 solutions here. So let's do that. So it follows then, since we found 2 solutions, and clearly they're linearly independent, these solutions. You can't make a cosine from sine by taking combinations. So it follows then that the general solution to our differential equation here would be a combination of our 2 solutions that we found. So C1 times cosine of x over x plus C2 sine of x over x. So that'd be the general solution of our original differential equation here. Okay, so we're done. So let's leave it there.